and I'm really pleased that many of you made it. I know some faces for formal methods and logic and reasoning, so I'm really pleased that the students made it. And it's a great pleasure to have Byron Cook giving this guest lecture on informal methods for system engineering related to logic and reasoning, related to automated deduction, and related to many things that we do at TU Wien. So one can say many things of Byron, and let me just put his affiliations right. So he's a distinguished researcher and vice president at Amazon. He's also a professor at UC London, and then recently he also started to work as a program manager at DARPA. And these are all sound impressive, but I think especially for us as researchers and academics, there are other things that impress us a lot. And let me put it in the context of formal methods. So many of you heard about the SMT solving and Z3 SMT solver. And actually, Byron was among the first ones who did the pre-version of Z3. It's called the Zapato SMT solver. So it kind of initiated logic and reasoning in the early 2000s. Then he also participated in the model checking efforts of ensuring or proving Windows device drivers error-free, and this was a SLAM model checking project. And if this was not enough, I think one of the biggest achievements of Byron in the scientific field is that we all know from Turing that termination is undecidable. It's very hard. And many people did not dare to touch it, but then Byron came and designed the Terminator tool and essentially showed that termination can be proven in many cases. So with all that, it's a great honor to have him here. He's going to do a very interactive talk, especially on a field that, again, as researchers, we are incredibly grateful because he kind of coined, I still think you coined the term of automated reasoning in the current industry. He actually found automated reasoning when he joined AWS back in 2014, and ever since then, automated reasoning is blooming in the industry. It's becoming something that went to Neurosymbolic AI, and you will hear how it went. So please go.
Thank you very much. Thanks for coming. My talk is probably like 45 minutes long, and I think we have more time than that. So it'd be absolutely fine to interrupt during the talk, and then I'm hoping you'll ask questions, or we can have a discussion, on the mic or off the mic. I'm around to talk for a while. So I actually came. I'm here because this morning there was a kickoff for this new doctoral school, and I was the speaker at that, and that's very exciting. So I'm going to give a slightly extended version of that talk, but with a little less time pressure, so I might also kind of add some more comments. I don't know if you know about the doctoral school, but it's very exciting and actually very timely. So basically what I did in that talk and what I'm going to do in this talk is I'm going to I have two reasons why I think that this is, my mental model is that most of you are relatively early in your career, like your master's students or PhD students, for the most part, looking around, that it seems to be quite youthful. And that many of you are considering careers or entering careers into formal or formal adjacent stuff. And I wanted to convey how exciting this field is right now. It's a really, really amazing and unique time. And so I wanted to convey to you why I think that is. The next thing I'll do is I'm going to tell you a little bit about why Amazon is interested in automated reasoning, kind of why it's grown at Amazon. And then I have 4 or 5 points to make that are quite forward-looking. So this talk is not about necessarily research that's done. It's kind of research that we're doing, and I think that, well, we'd be people working in the space, or a collaboration, or I'd be really excited to see folks here do research in the space too, and then we get to borrow the results or whatever. So, and we'd be happy to share kind of progress. A lot of people come do internships with us. I think we had 150 PhD student interns in formal reasoning last year in Amazon, all throughout the year, but especially during the summer. And so there's lots of opportunity for interaction. So anyways, I hope you enjoy the talk. So okay, so I'm going to make 2 points about why this area is super, super exciting. The first, hold up your hand if you know about the idea of the hype curve, or the Gartner hype curve. Great. So the idea is, this is published by this analyst firm called Gartner, which a lot of companies look to help them kind of navigate what's going on in the frontier of of the IT space. And so the idea is they publish these different curves for different technology areas, and one of them is in AI. And what's kind of remarkable right now about the AI hype curve is that Neurosymbolic is on the rise. So it's one of these technologies that people are getting increasingly excited about. And I see that with customers, I see that with analysts, I see that with the press, that people are beginning to click to this idea of Neurosymbolic, and they're getting increasingly excited about it. In time, it'll hit peak, right? And then everybody will be a little too excited about it, right? And they're going to think it's going to solve every problem they've ever had, and that won't be true. And so then it will, in time, slide down to the trough of disillusionment and spend some time there where everyone thinks that was, oversold and that doesn't solve any of the problems. And then in time, it'll sort of hit the medium where people appreciate what it can do and what it can't do. But what's amazing about it is that it is machine learning. It's our area combined with machine learning, and it turns out also that machine learning, there's a bunch of problems in automated reasoning that we can't solve, and so as the generative AI and agentic AI tools get more and more powerful, it turns out that they're solving some very important problems for us if you, like myself, consider yourself an automated reasoning person. So I want to tell you about that. But first, let's talk about just the roots, about kind of how this all came about. So it turns out that there was a workshop at Dartmouth College in the northeast of America in 1956. A bunch of people came, right? So John McCarthy, I think, sent the letter out saying everyone should come, and we're going to talk about, now there's this new idea of this digital computer, and they're commercially for sale. Like, what can we put intelligence inside of a computer? And you had folks like Claude Shannon, who did information theory. John McCarthy, you had people from the cognitive sciences, people from stats, and so on. And so that's really where the term was coined. And then sort of what happened is that, at the beginning, there was just kind of this idea of like, how do we like put intelligence in a computer and get the computer to do the sorts of things that we can do, and maybe more. And then over time, different branches formed, right? So you have the connectionist view based on models of how the brain works, and you have the Bayesian view based on Bayes' theorem, and then you have the symbolic AI based on mathematical logic. And if you had asked people in like 1963 what is AI, a lot of people would have said, oh, it's mathematical logic, right? That fell out of favor for a while, and so then there was a term like GOFI, good old-fashioned AI, which really meant mathematical logic, prologue, that sort of thing. But in time, the terms kind of evolved. So we increasingly called the statistical view machine learning, and we increasingly called the symbolic AI automated reasoning. I didn't coin the term, but I borrowed it. I was at Microsoft Research in Cambridge, England for 10 years, and next door to our building was the Cambridge Computer Lab. And there, like Mike Gordon, Larry Paulson, those folks had the automated reasoning group, and so I thought the name was nice. One of the reasons I really like the name is it starts with the letter A, and so we would show up alphabetically first in any sort of listing of scientific disciplines. I liked that a lot. And also, when I joined Amazon, I figured no one at Amazon would be opposed to automation. So like it sounded better. As opposed to formal verification, you have to kind of know what formal is to know what it means. And so I thought the automated reasoning was, I could have done formal methods, formal verification, automated reasoning, and I liked automated reasoning because it sort of set the ambition of kind of what I wanted to achieve there. So that's today's lingo. But what's really amazing, and I think the time, like how amazing it is to be your age and kind of being at the sort of the beginning of your career, is that these branches are coming together, and there's like really interesting interactions between them. It's actually pretty remarkable. And that's driven by the large investments we're seeing in generative AI and agentic AI. Now, I do believe that we're in a bubble, and I believe the bubble will eventually burst, and I think it's okay. So a lot of the people who kind of don't understand the tech will go away. But there's really genuine and interesting ideas there. And so while this bubble lasts, use that gravitational pull to get stuff done and get stuff funded. It will eventually pop, and we'll go through a bit of a dark period. But like the internet, like the railways, like radio, like television, I believe that the generative AI, is a fundamentally sort of a new technology that I think will have a lot of impact on us. Now, if you look at, here's just a sampling of different companies doing stuff in neurosymbolic AI. So DeepMind, like the alpha proof, alpha geometry, those kinds of projects, those are neurosymbolic. And like, for example, alpha proof, they're using the Lean theorem prover. Harmonic is a startup. I think they raised $20 million to go build formal reasoning tools. So they're using Lean combined with language models. DeepSeek, the Chinese language model, they also use reinforcement together with Lean. I'll tell you about the Amazon stuff. That we'll be talking about that today. And then there's another startup called Axiom that just became became known, and that they raised $60 million. So there's actually quite a bit of money being invested in the space right now. And there's others like Amandra and so on, but I didn't want to belabor the point. And then meanwhile, like the idea of generative AI itself, it's sliding into this trough of disillusionment, right? So if you look at the news, you're going to see lots of headlines around hallucination, and I've seen recently about like people using generative AI as a therapist, and that leads to pretty bad spots sometimes. And people making bad decisions, companies making bad decisions, and then there's lots of questions around: does it generalize, and can we afford to scale, and what's the sort of ecological impact and the financial impact on investing in these things at such a scale? And so it's just that what you're seeing is people are kind of like beginning to appreciate that these tools aren't going to solve all the world's problems, basically. I really like this one. The summer of vibe coding is over. Was a funny headline. But I mean, it's every day you look that you see. So anyways, if you're kind of entering into the start of a field, it's pleasant to be working on one that sort of like people have a lot of hope and optimism about, but also isn't completely overpopulated, unlike generative AI, which is kind of it's kind of on the downward slope, and it's a little overpopulated. Okay, so that's the first reason I think it's quite exciting. The second reason is that that we're going through actually a big paradigm shift. So hold up your hand if you know this book, The Structure of Scientific Revolutions by Thomas Kuhn. So this is a pretty amazing book. It's written in 1962, and it's the book that introduces the notion of paradigm shift. Like the word paradigm existed before in English language, but the notion that most people associate like of a paradigm, scientific paradigm, this book was the book that introduced it. And it talks about like the history of scientific innovation, and where basically new ideas like are in different models of how the world works are in conflict, and kind of the tension, but also the excitement that creates. So basically the idea is that science goes through these very long periods of stability that, maybe your advisor, or maybe your advisor's advisor, or maybe even before, kind of set the vision. And so, for example, in automated reasoning, the BDDs and then SAT solvers, first order resolution-based theorem provers, it was basically in the late 1950s, early 60s that a lot of these ideas kind of latched in. I think the first SAT solver paper was by Davis and Putnam, and it was a report to the National Security Agency. I think that was like 1958. So this idea of what we think of as SAT solvers, resolution-based theorem provers, or your higher order logic theorem provers like that, where kind of comes from like Edinburgh and the ML programming language, so it kind of comes out of that space. That area's been kind of pretty settled for a while. We kind of knew what the rules were, and then we were kind of like trying to bang away at those. Within that framework, we were trying to optimize. We're trying to make SAT solvers better and better and better. And cool, innovative ideas came out, but they weren't changing the rules per se. They were kind of living within the rules. And then what happens is from time to time, something happens and there's a major revolution. And so suddenly you have like a big paradigm shift, all kinds of new applications open up, right? There's new questions, but very exciting is new questions over old data. You can go over old data and old results and think about them like, oh, they mean something else now because of this new thing that's happening, and then new open problems, and then less what the book calls puzzle solving, that sort of within the confines of the rules that someone else has set, sort of like optimizing, or they also call it normal science. And so we're going through one of these periods, and the big driver in my mind is the move from the microprocessor to the data center being the sort of prevailing computational unit, right? So increasingly, Like if you look at the news, it's all about the data centers that are being built. At Amazon, I hear more and more about the data centers. And yes, we still use microprocessors, but people kind of think at the data center level, and they think about storage and compute as essentially as about as close to free as you can get. I think like S3 is like 2 cents per gig. So it's about as close, and the latency just gets shorter and shorter to read and write from that. So it's pretty remarkable. And so what is that doing to our field? Well, like slowly it's changing. I think it could have. Like a lot of automated reasoning is driven by these international competitions, like the international SAT, international SMT, SVComp, termination competition, you name it. And so the rules were, how do I say it? The rules were defined by the sort of old model, like it's a proxy. Like when you run one of these competitions, we're competing tools against each other because we're using them as a proxy for how they would actually be used in the field. Right? And so the requirements were you only got a dedicated microprocessor, 4 cores, this is an SMT comp, and then also quite disappointing, you're not allowed to read previous results, right? So you can't make an SMT solver that just stores all the proofs and then tries to look them up. You have to recompute. That's the rules of that competition, which if you think about it in the cloud era is insane, right? Like storage is so cheap. Why would you not just store lemmas and then read them? That's what you're going to do actually in practice. And you're certainly not like restricted to a single core in the cloud. Similarly, this is SVComp. You had sort of similar restrictions, also for termination competition, and a lot of the other competitions are the same. So the result is that you kind of have these bonsai trees, right? They're like exquisite in their ingenuity, but they're limited in their usefulness because if you actually are using them in an industrial application where you've got entire data centers, like if I told you you could solve the problems 10 times as fast if you could use the cloud, you can't use these tools for that. So, you know, but it's disappointing often because if I go to someone who's building these tools and ask them to add a feature that would make it work better on the cloud, they're often quite hesitant to do it because it'll make the tool slower in the competition. And but we're seeing this move over to the data center now. And so we see these new tracks in the competitions. Hold up your hand if you know Malib solver. So this graph is just totally mind-blowing. It's like unbelievably exciting to me. So how you read this graph is the following. So take this 100 seconds. The blue line tells us that there's a solver that can solve about 120 or 110 benchmarks each in 100 seconds or less. Right? So you don't want to be the solver down here, you want to be the solver up there because it means you can solve more problems. So we've run a bunch of SAT solvers against each other using the same benchmarks and the same hardware. And what's happening in this graph is that the lower half of the graph is all of the winners of the international SAT competition for the past 25 years, competed against each other on the same hardware and the same benchmarks. And then what the top solver is actually a distributed solver called Malib. And by moving to a distributed, so what's happening is you have many different instances of the solvers running on the same problem, and then they are sharing lemmas between each other. So there's a network topology where the conflict clauses, which are what we call lemmas and SAT solvers, are being shared across the network, and then at certain amounts of time, the solver is like pulling more lemmas from the network, doing a restart, loading those lemmas in, and then those lemmas prune the search space away. So a lemma learned over on this machine will cause you not to have to search more on this machine. And so the results are just absolutely mind-blowing, right? And this is just the first rev. I remember myself, well, I actually worked for a company called Prover, and we made a very successful commercial SAT solver, and then Chaff came along and just totally blew us out of the water. It was so much better. And that's this line, right? Like, I lost my job because of this line. Right, because our solver wasn't that good. So a bunch of people were using our tool, and then one day this open source solver came out that was so much dramatically better that suddenly it was like, well, why would I pay for yours? And so ultimately, I actually like changed employers because that happened. And I just look at this graph, and it's like, from my entire, I mean, I've been working in my career roughly 25 to 30 years. So basically, just by moving to a new computational model, without really doing a whole lot I'm sure, I know the Bellweb people did a lot of work, but I just think that like if you think about what's possible if a lot of people put their mind to making these distributed solvers faster, what's possible, it's pretty remarkable. By the way, Gen AI itself is also an example of a cloud-enabled or distributed. It's something that would only be possible with distributed systems, right? That's how, like, the cloud storage is how you store all the training data, and the cloud is how you run all the reinforcement learning, and how you have like zillions of GPUs all like training at the same time. That's only possible with the idea of a distributed system. So basically, you can think the move and the sort of like all of the libraries like Hadoop or whatever that people use when they're using the cloud, those computational abstractions are the reason that now we have generative AI. And so it's the move from the sequential microprocessor to, and so I mean, I've, you know, like when I was at Microsoft Research Cambridge, I sat next to the machine learning team, but they didn't have access to those machines. By the way, I'll tell you a story. So I remember once I was showing, so Laura mentioned SLAM. So SLAM was this tool that reasoned about Windows device drivers. It was based on predicate abstraction and counterexample guided abstraction refinement. And there was a time I was showing it to Bill Gates. By the way, Bill Gates, before he started at Microsoft, was actually in formal reasoning. And Greg Nelson's dissertation, so of Greg Nelson of Nelson Oppen, his dissertation was in 1979 from Harvard, thanks Bill Gates for introducing him into the field, right? For introducing him into the idea of like theory-specific decision procedures. So many years later, I'm at Microsoft and I'm showing him SLAM. Later, I showed him Terminator. And I remember we were looking at a graph where there were like 40 properties and like 40 device drivers. So there was like a big graph of all the results on the device drivers. Like we proved these properties and these properties failed. And Bill Gates looked at me and he's like, would you want that many machines, right? Because now I could, he's like, how long did that take? I was like, oh, well, hours, because we had to run them all, you know, and he's like, do you want a whole bunch of machines? And I'm like, no, absolutely not. Because at the time I would have had to go update them all, right? So like there was no notion of cloud and like cloud scale updating. So that all kind of came a few years later. So if I had been asked later, do you want cloud credits? Like, of course. But so that was just, so those of us in the research labs at the time didn't have a data center cloud mindset. We had the machine under our desk mindset. And so it really sort of limited the kind of research you would do. And so generative AI, you see it really beginning, it's like, you know, I think the AWS came out in like 2005, 6, something like that. And so then like, I mean, that's only a few years later are you seeing the rise of generative AI. So anyways, so this graph is kind of showing the models getting bigger and bigger, and then what we have all learned, and I'm sure we've all kind of read in the newspaper, is that with the models getting bigger, they have these sort of like incredible jumps in their ability to like perform, right? And so that's pretty amazing. What's also amazing about it is that they are trained over, like 4 years ago, all of the models began to train over Lean because the world of mathematics began to use Lean, like Terence Tao and so on. And so that became training data. And then what people discovered is that the Lean training data was actually really good. And so then what they began to do is to synthesize more and more Lean lemmas, right? So they would like make conjectures and then prove or disprove them, and then use that as more training data, and that made the models even better. So then they combine that with reinforcement learning, and the models get even better and better. So what's happening is that the language models, most of them are trained over quite a bit of Lean data, and that makes them actually very good at running theorem provers. So you can these days ask a model to write you some code, but also ask it to find the inductive invariant for you, and ask it to find the ranking function, and ask it to find the rely guarantee constraints. And they'll be wrong from time to time, but what you can do is now map that into the theorem prover and then use the theorem prover to prove it. And if the proof doesn't go through, then you go back to the language model and explain it didn't work. So there's a new loop. So there's basically, via generative AI, there's sort of a new way of proving stuff. Like we can use all the old stuff, like abstract interpretation, predicate abstraction, interpolation, all those, by abduction, all those tricks still exist. But those were heuristics, right? And they were heuristics developed like by people like us based on, the programs that we were trying to get the proofs to go through with. But there's sort of a new vector or a new way of solving these that complement that. And that comes from the world of generative AI. So that's very exciting. So basically, there's a sort of a new method of formal reasoning together with a large language model that we all happen to know has a lot of lean inside of it. Okay, so that's sort of that's the two reasons why I think it's pretty neat time to be entering the field. And so enjoy. So let me now tell you a little bit about why Amazon's kind of been in this space. So it turns out we use a lot of automated reasoning. All of the executive team at Amazon is well aware of it and big fans of it. And sometimes there are teams that aren't using automated reasoning, and the other vice presidents from EC2 or the storage team will say, I don't understand why you're not, and kind of push them on it. So it's been, I've been at Amazon for 11 years, so it's been approximately 11 or 10 years, depending on kind of how you count, that we've been investing in it and basically doubling down every year. And during the Q&A, I can answer questions about kind of what that process looked like. Simultaneously, I don't know, like OpenAI started, they announced themselves December 11th of 2015, right? And so AWS was actually an original partner with that. AWS was very interested in this idea of the transformer models and what could be done. And so we were excited to see kind of what this organization could do. So we invested a bunch of money in compute. And then at the same time, right, we being AWS invested in automated reasoning. So what you see happening is that Amazon is trying to look around the corner on behalf of their customers for what kind of technologies could they invest in that they can then use to increase security, increase correctness, lower costs, these kinds of things. So these are various kinds of bets that were taken, and they were taken by customer requirements. So when you talk to customers about the cloud, a lot of questions are coming up around privacy and sovereignty and security and availability, right? And a lot of those questions that come up are universal in nature. They use terms of logic and temporal logic, right? Like always and eventually and for all, right? And so these are the sorts of questions that you're typically going to hear. And then if you look at those questions and think about what they range over, it's enormous, right? So this question here ranges over all possible AWS policies and all possible requests to AWS. So what that means is, like, if you think about AWS, it's a whole bunch of resources available on the internet, like machines, storage units, and then there's operations you can make on them. So you have different principals, you can have different AWS accounts and sub-users, and you can assume roles into other principals. And so every call to AWS, if you, like, from the command line, if you do AWS S3 LS return, what that's saying is, like, as the principal I'm currently logged in is, go to S3 and do a LS, like a listing command on the top level bucket. And so then what happens is the AWS in the cloud is taking all of the policies relevant to the resource, in this case S3, and all of the policies relevant to the principal, in this case like Byron's account, puts them together, and then it calls a policy interpreter, and then it makes the decision, should we allow that action to take place or not? And so that set of policies, the policy language is basically a version of first-order logic encoded into JSON format. So there's going to be limits. So there's going to be a finite set of policies, but wildly intractable, right? And then the next thing is, what are all possible requests? Well, the size of strings that you can pass to AWS when you're making a call across the internet is enormous. So one time I did the arithmetic, and it's like so many, like if you had more microprocessors than you could possibly imagine, more microprocessors than exist on planet Earth right now, even that it would take like thousands of lifetimes of the sun to exhaustively enumerate just all the possible authorization requests, even with a fixed policy. So there's no way there's no way you could answer this question by just enumerating all of the inputs. So what the bet that Amazon took 10 years ago is like, well, why don't we use like SMT solvers? So we encode the questions that one has like this into SMT, and then we're able to expose that to customers. So this is a feature that's available to customers actually for free that they can use to understand their policies before doing deployments. We have also similar capabilities in a AWS service called Managed Configurables, and then there's also S3 Block Public Access, which is basically an adaptation of IM Access Analyzer to S3. And these are all of these are powered by an internal thing which we call Zelkova. So Zelkova basically encodes the semantics of the AWS policy language into logic, and then we can compare different policies and ask questions about which is weaker or stronger than each other. And so we use that a lot internally, and then we use that to power these services. We also have a customer-facing feature called VPC Reachability Analyzer, and another one called Inspector, and there's some others, and a bunch of internal stuff. But they're all using this thing called Tyros, which is again an encoding of the semantics of EC2 networking into mathematical logic, and then we use solvers to answer questions around reachability. And then we also do these. We prove a lot of stuff about our source code. So for example, AWS Clean Rooms, that's a service, but also a bunch of internal stuff uses an idea called differential privacy. And that's a sort of statistical technique such that you can look at sort of populations of data, but not learn anything about any individual in the population. And you're going to want to really get that technique right. And it's hard to get right. So we in the lean theorem prover, we prove the correctness of the foundations of that code that's used in clean rooms. And then we also prove the correctness of the cryptography. There's a very nice talk about the correctness of the proof of that policy interpreter. Remember, I mentioned that whenever you call AWS, we call this policy interpreter. Well, that's some code, and it was called Balsa. We replaced it with something we called Yucca. And we proved it correct. It also turns out to be 3 times faster, right? And that's actually called 1 to 2 billion times per second, which is kind of mind-boggling. Like that, AWS is called 1 to 2 billion times per second. So like already there's been billions of calls to AWS already. And what that is like everybody who's using AWS is making all these calls to AWS all the time. And so every time that code that's in deployment has been proved correct, it's written in Daphne. And what did we prove? Well, we proved its correctness against the Zelkova semantics. So we proved that the Daphne code basically has this property. We do this for a lot of other parts of the system. So we've reasoned about S3's semantics, for example, when we move from eventual consistency to strong consistency. We reason about the hypervisor stack, virtualization stack. We reason about, there's another policy language in a service called Amazon Verified Permissions, and there's a policy language called Cedar. We also do reasoning about that. And there's a lot of other stuff going on. So basically, it's increasingly ubiquitous amongst around Amazon. And then because all of the other AWS service features are built on cryptography, networking, virtualization, and storage, then by transitivity, if you will, all of the AWS services benefit in some way from formal reasoning. And so it's people often are wondering kind of like what the economics of this thing are. And I have a whole talk about the business of proof, but in summary, the customers really wanted this work. Like a lot of customers moved to AWS because of this work. And a lot of customers moved a lot more workload to AWS because of this work. Because this, for them, was very differentiating, and it gave them extra security that they couldn't achieve in the clouds that they were thinking of moving to, and certainly in the data centers they were operating on their own. And so one of the big surprises to me, and I guess one of the big lessons in my life, because I had worked previously on these kinds of tools, is that how important soundness was to leaders. Not necessarily hands-on keyboard people using the tools, but the leaders who are writing the checks, right? The people who are like paying for these tools or moving or making the decision to move to AWS. the fact that we can clearly articulate what is true and untrue, or what is true and what we don't know, is actually very important to them. And so soundness turns out to be something almost, maybe so sound is too strong, but to me it's not. It's almost sacred. It's sacred, right? And so I end up as a part of my role in Amazon reminding scientists that how important soundness is, because often, when you're trying to chase results, you're kind of willing to give up on soundness. So an example of this is in SLAM, we did cut a couple corners. We didn't treat arrays correctly, and we made this very weird corner cut that really was very helpful. We assumed you would never call a procedure in C both by function and by name. You could only call it by name or by pointer. So by pointer or by name, but not both. And if you made that assumption, then SLAM suddenly became 40% faster. But it was unsound. So in theory, right, you could have a function that you called both by pointer or by name. It was unusual, but you could do it. And then also arrays, just we didn't handle arrays at all. So if you did x1 gets 5 and x2 gets 6, then x1 would be 5. And the reason was because you really didn't see arrays using device drivers very often, but they could. And so then the problem was that now you talk to an executive at Microsoft, and they're getting kind of pumped up about formal, and you're having to like, well, hold on, it's not really true, right? And so you basically are always sort of like too cautious about what you can say because you've cut corners, and so then the energy doesn't come back to you. They end up not funding your work because they're like, oh, if it's just bug finding, then we've got a whole bunch of penetration testers that are finding bugs. So I guess I'll put you in sort of that camp, and they think about how to cost it or how to fund it in a really different way, and so it turns out to be kind of destructive. So it's for what we heard very early from AWS customers is how important soundness was, and so that's a big area that I drive on. Happy to take questions about that later on. Okay, so now what I'm going to do is I'm going to talk about some research directions. So so I think we all kind of know probably the story about like OpenAI and Anthropic and the sort of the sort of OpenAI. I mean, it was a Google and then OpenAI and then a diaspora to companies like Anthropic. And so that's been kind of an amazing past, I don't know whatever that is, 10 years. And then meanwhile, we were working on the sort of dual side of that with the formal reasoning at Amazon. And so what's happened really is the two worlds have collided, and I've already kind of alluded to this. But how did that show up for me? Well, that showed up by the questions customers were asking began to evolve, and we began to hear a lot more about correctness of agents, trustworthiness of agents, hallucination causing incorrect results on chatbots where the chatbots were being applied in areas where correctness really mattered. And then amazingly, the society discovered truth and specification, right? Like these were not concepts that I think a lot of people understood unless you were here taking these kinds of courses. But for like your general public, suddenly there was a societal level discussion on what is truth and how do you write down what you think should be truth. And so we're kind of as a culture going through that. So I'm going to basically talk about some research directions that address each of these, and then there's a few other things that kind of fall out too, and so I'll mention those. So let's talk about Q&A correctness first. So imagine you have a chatbot, right? And you're like the city of Portland, Oregon. This is the demo. This was actually the demo that we used that we showed that funded the product that I'm going to tell you about a little bit. So imagine you're the city of Portland and you put this chatbot out, and the chatbot is allowing the population, the people, the city dwellers, to ask questions around construction. So there's this idea called an accessory dwelling unit. It's like a small house in your back garden that you can build. And so imagine you get an answer from the chatbot, and imagine that the answer is from a large language model. So hold up your hand if you would just call the contractor and start digging up the backyard and building the house without doing any further double checking on this result. So I'm just, hold up your hand if you would not take action on this result. Yeah, there you go. So yeah, so that's what that was the problem that all customers were having. Is that, so a lot of customers were like, wow, Gen AI is super cool. We're building these demos. They look really great, but we totally can't use them right now. Right? So what do we do? And so we were like, oh, actually, that's like, they're asking for formal verification, right? How amazing. So, so the answer depends on reasoning, right? Over the zoning rules from the city of Portland. So the trick now to make this accessible is how do you translate from natural, because these rules are going to be written in natural language. And the people writing these rules and thinking about these rules, if you go to like Portland, Oregon, and go to the city building and go find the person who's in charge of like, whoever's in charge of how wide the sidewalks need to be, there's someone who owns that, or how far back the trees need to be from the sidewalk, or these kinds of things. That person has not studied, you know, Hilbert's epsilon operator, right? Like, so we're going to need to use the language that they know, and that's going to be natural language. And so the thing that's sort of really emerging is how important this mapping between the natural language and the logic. And so it goes by various names. I think auto-formalization is a little too strong because I think that actually you need a little bit more human in the loop often. But this, I think of it as like as a logical twin, not a digital twin, but a logical twin, right? Where you have the natural language, you have the logic, and there's a relationship between them, and you're trying to maintain that relationship or trying to figure out what that relationship is. And there's this really amazing opportunity where you can get a large language model to go over a whole bunch of like text and then encode something into logic for you. It might not get it right, but if you have a really amazing user experience, if you can help the human who understands natural language only understand what's in that logical formulation, then you can get them to sign off on it, and that becomes knowledge, right? So like, there's knowledge, and then there's sort of like data, right? And to lift it from data to knowledge, and to be able to generalize that and say, oh, these are now the rules. Like, this is the rules of the game of chess, or this is how you play Go, or this is how molecules connect to each other. These kinds of like the knowledge or the theory or the models or the theories that we have about how the world works. If you can get that automated and encoded, and then get someone to look at it and to understand what's in it, and then say, yes, that's right, that's a very powerful experience. And that's kind of what we're after. The other thing we're after is at inference time to help a human who's like asking a question to help get that translation right. And so here what you really need is like a theory of mind, right? So when you're talking to people, you have a model of what the people know and what they don't know. Like, you'll kind of learn, like if you're talking to someone you meet, like a friend's friend at a cafe, and they're asking you what you do, you're going to give a very different answer to what you do than if Laura asks you what you do, right? You're going to give a much more technical answer to Laura. So you have a theory of mind. You have like a mental model of what they know, and then you may ask certain questions and see how they respond. And if they respond in the right way, that means you can tell them a bit more. And if they ask follow-up questions, you can also sort of judge if someone understands what you're doing based on the amount of follow-up questions and so on. So that's a sort of iterative process, and that's something we've been doing as humans for eternity, right? So here's a picture of my wife talking to a friend of ours in our back garden. On the right, my friend talking to her dog. And then there's me with my great-grandfather, right? So he's asking me questions knowing that I'm a child at different levels of abstraction than he would be asking. And he's also trying to evaluate what I know and what I'm thinking about and kind of what my mental model is. And if I'm like crying or I have some problem, he's trying to evaluate what that is. So this is something that we do a lot. And so we have a bunch of tricks as a society to do this. So there's the idea of active listening, and there's this idea of like the Swiss cheese method, right? Where you kind of say the same thing a bunch of times different ways, and then hope that the person listening is able to synthesize what you're trying to say from the different attempts. And so, in this world where we're working with bots, this is where we're going. So an example of this is, here's a customer example. So this is an airline. Very early on when we were working on one of these products, an airline gave us a whole bunch of Q&A pairs from their customers, and this is one of them. And so we can translate that into logic, but the likelihood that this translation is sound is going to be pretty low, right? So what we do is we do the Swiss cheese method. So we actually translated a whole bunch with different language models or different configurations of the language model, and then we use the theorem prover to prove that each of the translations are equivalent. And so the more we do that, the more and more comfortable we get that we got the translation right. So this is one of the ways that we're tackling that. And then let's imagine that there's a difference, so entailment doesn't, or so the equality doesn't hold between them. Then what we can do is we can find the difference between them and then pass that back to the customer's customer and ask them, what did you mean, right? So was this a trip that you've missed, or is this a trip you're going to take, right? Did you want that flight to be coach, first class, right? Are you going to Portland, Oregon, Portland, Maine? These kinds of things. And so that's a form of active listening. Okay, so that's one area of research, and in a bunch of in Amazon, there's something like 20 automated reasoning teams across storage, crypto, the LLM vending out, the team that vends out large language models, also the Agentic AI team, the people who train the large language models, and there's a whole bunch of work and all these teams amongst the, 300 or so people who do formal reasoning in Amazon, where this is kind of an area that you just see people beginning to work on. The different teams are using each other's tools, so this is kind of an active area for us. And so if you're looking for research topics, I think it's a good one. Another thing that comes up is about the customers will ask, hey, I built this really great chatbot using your tool for this problem, and then I built this other tool for this other problem. And then they're like, well, can we combine them? What if their customers ask questions about, at the intersection of zoning laws, tax law, and mortgage approvals, right? Can I build a home? How much am I going to pay in tax on it? And I think it's going to cost this much, so could I get a mortgage for it all at the same time? And so one could imagine a marketplace evolving where maybe the mortgage folks provide a formal model for when they'll approve and when they won't, and then you have a formal model for the zoning, and then you have a formal model for the tax, and maybe different providers provide them, and then you put them together. And so, naively you would just use conjunction, but the challenge is that the formal models might be, if they're axiomatized over variables, the variables might not align. So there's some challenges around how do you synthesize from natural language to a formal model such that it's composable with other formal models, and so that's kind of an active area for us. In terms of truth, I wanted to tell you a story that's a very common story. If you go off into your career and apply formal reasoning, automated reasoning, whatever you want to call it, formal verification, to real problems, this will be a story that you're gonna. If you don't already know this, you'll learn it. So Zelkovo is the thing I mentioned. It powers the IM Access Analyzer and S3 block public access. It was written by a couple people early on. I'm using photographs of toys from my childhood rather than the real pictures of the real people to sort of protect the innocent. But we had an identity expert and we had a formal methods expert. And luckily I had a toy with a formal top hat, so that's good. Okay, so what always happens is, we ask the domain expert, okay, so we're going to build a formal representation of this world you're kind of operating in. And so we ask them for, documents and at the whiteboard and these kinds of things. And then we go off and try and formalize it, right? And then we run the tool. We have a tool, so maybe it's based on a theorem prover, maybe it's based on a model checker. And we run the tool and we get some answers, we get some yeses and some nos, and we go to them and we say, here's a bunch of bugs we think we probably found, and then invariably they're wrong, right? Invariably they're like, oh, no, that's not a bug, that's fine. And here's why, and they're like, yeah, but you didn't say that. I'm like, oh, yeah, sorry, I forgot. And then, right, and so then we refine the abstraction. And you'll end up going around and around many times. So in this morning, the talk, I kind of mentioned this, that when I was at Microsoft Research working on that SLAM tool, much of my time was spent on the shuttle between the Microsoft Research building and the building where the Windows kernel people were doing this, right? I was like, oh, I found some more bugs, and they're like, no, it's not a bug. Why? Oh, okay, why didn't you say that before? So you kind of iterate round and around. And so that's my entire career is this story. So I worked on hardware, worked on device drivers, I've worked on models of genetic regulatory pathways, I've worked on virtualization, I helped the team start to do the storage stuff, I've worked on railway switching correctness, and it's always the same story, it's the same thing. And so something that we're really excited about is the idea that you might be able to use generative AI here, and so it's not going to work out of the box. There's going to be a bunch of stuff we have to do, so I'm going to tell you a little bit about that. So we have this product that we launched called Automated Reasoning Checks, and it helps customers build formal models for chatbot-like applications and then deploy that and then remove the incorrectness at inference time. And so the big challenge is this problem. And we can't basically send an automated reasoning scientist to each customer and spend a year with them, right? So to really scale this out, we're going to need to do something better. And so that's where the generative AI comes in. So the product allows you to upload files. So we're currently taking PDF files. So you load that in. It calls a generative AI. And it takes a swing at the formalization. So this is an axiomatization of a customer's rules expressed in natural language, sort of in pidgin English. It's actually an SMT lib, but we map it back to English for them. And then here on the top are the variables over which the axiomatization is axiomatized. And so then we can now hand them a bunch of disallowed, allowed and not allowed examples, right? So here we're showing them an example. This would be allowed in your model. Is that okay with you? Right? And they can say no, and then they can give us some natural language feedback on why it's not true, why this isn't right, and then we can take that back to the language model and ask for help, right? And so if you kind of understand logic and kind of think it through, you're going to be like, whoa, there's going to be a lot of examples. And so we have some techniques where we build equivalence classes of them, and we find one example, and then we block that, and so there's a bunch of tricks that we're trying to do. Actually, kind of borrowed from IM Access Analyzer. Actually, that was one of the products that's built on Zelkova. We kind of have a similar problem there. And so we find an interesting and representative set of examples that are allowed and not allowed to give the expert in the domain the ability to understand kind of what the specification is saying. And then the other thing we can do is we can launch that and then see how customers are using it. And if they flag certain answers as not correct, we can usually track that to the exact axiom that's the problem and refine it. So anyways, that's pretty exciting work. And then they can review the policy changes and so on. We have sort of similar work going on with there's a new IDE, a generative AI, agentic-driven IDE for developers from Amazon called Kiro, and they were really influenced by our work. So this is their motto: the flow of vibe coding with the clarity of specification. It doesn't have, you're not able right now to write LTL or CTL specifications, but one could imagine that might be coming, right? So it's not escaped our notice that we could do that kind of work. And so here, for example, maybe you, in natural language, like it should eventually be true that P is set, or P is some variable, and then stays set, right? So this is a temporal specification. And so here, for example, is a linear temporal logic encoding of that property. Right? And so one thing we could do is we could show them a bunch of little programs that would respect or not respect that property. So the little green programs, the property is true, and the little red programs, the property is untrue. Right? And we could show them the morally equivalent branching time temporal logic encoding of that same property and show them, again, the little programs, and then you'll notice there's a difference. Right? So the morally equivalent LTL and branching time temporal logic version of this property, there is a program for which the one property, the linear temporal logic version holds, and the branching time version doesn't hold. Oh, that's super interesting. So even though they don't maybe understand logic, but they know code, they could say, well, I actually want the property to hold. So then they clearly want the FG, and so they could say, okay, so that's my logical twin now, right? And so this is the sort of refinement process that's beginning to emerge. Another challenge that you're going to find if you go off and apply this in industry, and I hope we can make this much better for you, but certainly it's been in our career, the big challenge is that everyone is like, oh, your tool sounds super great, but I write code in, Kotlin. Does your tool handle Kotlin? No. Oh, okay. Well, not interesting. Or I write in ARM instruction set, or I write in C++, or it's like, well, no, my tool only handles this other language. Oh, okay. So an area that sort of, to make this very real, is to have an intermediate representation that can sort of handle all of the programs that make your life really good for formal verification. So together with with several other companies that do neurosymbolic AI, which I'm not sure if I'm allowed to name because I don't think they've been announced, we're jointly developing this idea of CSLib, so a whole bunch of programs and with properties and proofs, and then we're contributing the language for which the programs will be the intermediate representation. So you can handle ARM instructions in JavaScript and TypeScript and Python and SQL and Rust and you name it. Okay, so 2 or 3 other kind of areas, directions that I think are interesting. So hold up your hand if I told you that there's this new amazing agentic tool that is, so long as you give it access to your bank accounts, that it's going to make really smart investment decisions for you and send money to your parents when you make a certain threshold. Are you going to just gleefully give away your bank details to this agent? Hold up your hand if you would not do that. Right, exactly. So that's the problem we're trying to solve. So AWS has a couple of products kind of headed in this space. So one of them is open source, it's Strands, and then there's also an AWS service called Agent Core, which is developing an environment in which agents would run and in which we can control their behavior and set boundaries and guidelines and sort of semantic guardrails and to allow you to specify what would be good things and bad things. So it turns out that this is in the area of formal reasoning. I don't know if you've encountered this in your studies, but there's this idea of compositional reasoning. So for distributed systems or concurrent systems, you can use Lipton's movers, you can use rely guarantee style reasoning. There's a whole bunch of ways where you can reason about the composition of threads or composition of programs, but never have to think about all of them at the same time, right? All the possible cross product of all the possible interactions. What you do instead is you reason about one thread, and then you reason about another thread, and you reason about another thread, and then you build an environment model abstraction for what the other threads could be doing while this thread is running. And if you can kind of figure out how to do those proofs, it makes the area a lot more tractable. And so basically there's applications of this now to agentic systems, because multi-agent systems are basically compositions of these systems. So we actually did this in the S3 service where we had models of all the protocols that are being used in S3, and then we were able to reason at that model level that when you composed programs all following those protocols, that then strong consistency would hold. And then what we do is we actually, at runtime, we actually just do runtime verification. We check that the programs are respecting those protocols, and then, sev to the team. We page the team if it's not true. And so we kind of have a similar model here in mind, that we can reason compositionally about availability, security, privacy, durability, these kinds of things. And then what we need is like a runtime enforcement for the actual agent, because the agent is an LLM generating commands. And so we're looking at using Cedar, which is this policy language together with formal reasoning capabilities. So the idea is you have a large language model generating commands for a microprocessor, and here's a little picture of a microprocessor. And so what we would do is we would interrupt them and do reasoning using that formal model. So that model, think of that model as like a language. And so are the commands coming out of the LLM allowed by the language of the property that's the specification? And if so, we'd let it go to the microprocessor, and if not, then we'd push back and go back to the language model and say try again. And so the idea right now is we're using Cedar. There are some challenges with doing that. Cedar doesn't really have a notion of temporal logic, but one could imagine extensions and so on. Another area that's really big for us and really big for a lot of folks in the development space is agentic developer tools. So AWS has all these products, and all these teams are wildly embracing generative AI right now. So there's several teams that have completely redesigned how they're writing code such that they can integrate generative AI quite deeply into their system. So it's very viral within Amazon. A lot of people are tracking that. There's this one project that they've done this, and it's been quite visible, and they've given talks about it, and people are kind of tracking how they're doing that. And so people are pretty excited about it. And one of the reasons they're really excited about it is every person on the team has experienced a 10x productivity boost, right? They're like, oh my God, suddenly I was getting so much more done. So we really like the look of that. We also like the look of that because it moves the socio-technical mechanisms we've been using before, and and sort of opens up space for doing formal reasoning, right? So here, for example, we have a blog post that's talking about how whenever we use formal reasoning, it seems like the programs are faster because ultimately the people writing the code feel freer to be more aggressive, to write more aggressive code. And so we're seeing that a lot with Agentic AI, that you can use Agentic AI to optimize your program, and then we can prove equivalence between the old code and the new code. And then one could also imagine doing properties. So for example, in AWS, we reason about the data flow across services, right? Does data flow from the EU region into this S3 bucket through this Lambda to this Dynamo table and then go to Virginia? Or are there like some core controls so the data can't leave the EU region? And we're able to prove that automatically with some tools. And then when you combine that with Agentic AI, it allows the Agentic AI to be used relatively fearlessly. And so that's, I think, starts sort of a flywheel where the more we see Agentic AI used in coding, the more demand there's going to be for formal verification. So, but there's a lot of work to be done. So imagine we begin storing proofs. Like I've proved the correctness of a program. I don't want to go rerun the proof every time I make a modification to the program because now maybe you have summaries for all of the other APIs that it's calling. So you're going to want to do like incremental proof repair, if you will, right? If the code changes. And so that's a pretty open area right now. There's not a whole lot of work in like how do you take a program that's been proved, but now the program's been modified? How do you go, do you like pass the old proof to an LLM and ask the LLM to discover a new proof? Or do you have some very clever representation and then you break the proof a little bit and then allow your old procedure to incrementally start from where it was before? And those are all kinds of open questions. So we're currently doing this for SMT. So we have a whole bunch of solvers operating, and then we like that Malib tool I was telling you about, where we basically lifted that to SMT. But then where I would really like to see things go is, maybe you have a data flow, data log, SMT, Vampire, SAT solvers, Hololight plus an LLM, Isabelle plus an LLM, Lean plus an LLM, and then all these tools are operating together, and then maybe they're all speaking ultimately in the Strata language, right? Where you have your program's written in Rust, your program's written in Java, your program's written in C++, it goes to Strata, and then from Strata we have deep embeddings into Isabelle, to Lean, to Hololight, to SMT, to Vampire, you name it. And then so the final thing, I want to talk a little bit about soundness and some of the implications in neurosymbolic. So it turns out that soundness is both a technical but also like a cultural thing. Right? So it takes actually a lot of effort to keep people on the straight and narrow when it comes to soundness. So one of the things we do at Amazon is we have a quarterly meeting where we randomly choose one of the automated reasoning teams in Amazon, and then they present their soundness strategy to the rest of all the other automated reasoning scientists. Right? So here, where it's being announced that the next one will be December 11th. This is an intro you can't attend, but. Well, I think I saw one or two Amazon people, so you can. But anyways, this is an internal thing where, and this time it's Lean. So the Lean team will bring a document that they've prepared that they've gone through a process where there's a review process and so on, where they describe all of the risks to soundness and then the mitigations they have for soundness. And then we talk about those and we learn from each other. And these meetings are extremely well attended and extremely exciting. So this is the kind of thing we do. We also work, a lot of our science is actually directed at this challenge. So here, for example, is a paper that's about how do you run a distributed SAT solver and then get these different proofs in DRAT or LRAT or whatever, and then combine them together into a proof for the whole thing. So that turns out to be very important to us. Another example of that is we worked with the CVC5 team to add proof. And in fact, CVC5 is basically CVC4 plus proof production built in. And that was something that was quite important to us. And so we worked pretty closely with them. Now, the challenge is, in this new world of neurosymbolic AI, that things are a little trickier, right? So, the translation, I don't have a theorem to point to here right now, but it's my intuition that you can never be sound for natural language. There's just too much ambiguity and too many ways of like hiding information deep in the language. It's just, the language is too unstructured to ever have any sort of soundness guarantee. So it's going to have to be something you measure, right? It's going to have to be something that like almost you have like a jury to decide whether or not we got the translation right, and I know it when I see it, kind of thing. So it'll be a challenge, but for us, it's really important. So this quote I like and use a lot is that the test of a first-rate intelligence is the ability to hold two opposed ideas in the mind at the same time and still retain the ability to function, right? So the idea is like soundness is super important. That's our tenet. That's why we're here. That's why we're paid. But on the other hand, we need to make these tools useful also. And so you can't just always say, I don't know. And so that's the challenge. And then particularly if you introduce the idea of neurosymbolic, where you're doing translation from natural language into logic, you've really lost the ability to actually be sound. And so now you're going to have to like bang away at it. And so the idea here is that can we achieve 99.999% soundness on a suite of benchmarks? And this is very common in the cloud distributed systems world for availability and for durability, right? So different AWS services will publish their nines. How available are they going to be, right? And it's an important thing that customers take a dependence on. And so it's actually a fairly common concept. So right now, automated reasoning checks, we announced it was 99% verification accuracy. And how did we compute that? Well, we ran it on a bunch of benchmarks from this conditional Q&A benchmark suite. And then we also did this for a bunch of internal customers that were early beta testers of the tool, and we hit 99%. So then we were pretty excited about that. But the thing is like measuring soundness is a little trickier than you'd think, because I also mentioned this idea of theory of mind, Swiss cheese, and the active listening concept. So you kind of have to measure valid at in, where maybe you have to take a couple swings at trying to understand the question, right? So I didn't quite understand the question. I still don't understand the question. I still don't understand the question. And you can see valid going up on the different rounds. And so this is data. There's a paper that I think will be on archive soon that's about this product. And this is kind of where this is the measure that we're currently finding useful to measure our progress. Okay, I just have one last slide. So I've dumped a lot of information on you. There's stuff you could go click on and watch if you want. On the top left is a talk I have given, actually here, I don't know if that one was recorded, but I've given the version of it a bunch of places, called The Business of Proof. I think the best one's the one I gave at University of Washington. But the point of the talk is like, why did Amazon invest so much in formal reasoning, like culturally? So I talk about some of the cultural dimensions that made formal reasoning successful in Amazon. And then what's the business model? It turns out that Amazon is a low profit margin, high volume business, and it turns out that in that setting, if you're doing business to business, it turns out that formal methods is really super compatible. Whereas if you're doing a consumer business, maybe it's a little less so, and then if you're a high margin business, maybe it's a little less important. So at Amazon, it turned out to be kind of the sweet spot for formal. So I described that in some detail. At the bottom left is a blog post about some of the challenges I mentioned here today. It identified, like for example, this Swiss cheese idea. We described that in that blog post. On the right the top right is this paper about high performance and proof being comorbid, and then on the bottom right is a Q&A that I did about 4 weeks ago with that's Karina Hong. She's the CEO of Axiom Math, which is one of these neurosymbolic startups. So she raised $60 million from Madrona, and so the Madrona venture capitalist, one of the people who funded her, is doing a Q&A at this event for startups, and so it was she and I on stage. Okay, so with that, thanks very much, and I'm happy to take questions. I think we have.
Questions?
That's one, yeah.
Hi, thanks for the talk. I have a question concerning the figure you gave on the different SAT servers, right? So you were saying they were all compared on the same hardware, same setup, right? But the cloud one obviously was not.
Yeah, exactly. Yeah.
So I'm curious, like how many, what is the cumulative time of if you take all the different threads to run or something like that?
Right.
Or yeah, how many parallel servers was that?
Yeah, so it was the same microprocessor, but there were many of them. And the compute time is going to be much larger. So you're going to use way more energy, way more compute. So it depends on kind of like if you're comfortable. Microprocessors are ridiculously cheap these days, so you can have thousands of them, no problem. If you really need SAT at the edge, like imagine you're doing something behind the moon, you know, so that you can't get in radio communication with the cloud for a moment. Then that's a different application. The thought I have, and this is, no one has implemented this idea, but I think it's quite interesting. One could imagine a local SAT solver also, right? So you on your machine, you call the SAT solver, and it is a SAT solver, but it's also calling to the cloud. And so if you solve it before the cloud even comes back, great, just give the answer. So there's no cost of latency. But the other thing is you could train the heuristics and change the heuristics on the local solver, right? So if you find a proof very quickly with the distributed solver, there is a sequential proof there, right? Because decision was made on this machine, decision was made. We found a conflict clause, we added it, that pruned some stuff, we were able to prune some stuff, yada, yada. And so that means there is a set of decision heuristics that would have, on a sequential microprocessor, given you the same performance. So can we learn what those heuristics are and then actually bring them to the local solver? So that's a thought I have, but completely unimplemented. So.
Thanks.
Hi. There is this charming story, I don't know if it's true, about Kurt Gödel at his naturalization hearing in the United States, that he kind of was convinced that he found like an inconsistency or something in the American Constitution or whatever, right? And this reminded me a little bit on the formalization mining and the back and forth with the domain experts and the formal people. And I wanted to ask, how often is it the case that by formalizing this expert knowledge, there are like some things that are actually like uncovered that are logical inconsistencies or that have been worked around or that just don't happen in practice? Or I wanted to get like some insight on this part.
Yes, I have a bunch of thoughts there. First of all, and law is a little tricky because there's epistemic and aleatoric uncertainty, and so the different legal systems, like the French and the British legal system, are actually different. Where the French, like the Napoleonic countries, encode things more, and then the common law versus civil law. So there's different forms of uncertainty, and we can encode some and others we can't. First of all. Secondly, there's some interesting cases where in tax preparation, if you are seen to be using these kinds of tools, that is actually cause for the tax authorities to come after you in the US, at least. So one has to be careful about tax. But then there's this really neat startup, I'm going to mess up the name, so Ruzika Pislich, yeah, and Scott Shapiro have a startup called Leibniz AI, that's doing this for, they both have a language model trained for legal reasoning, and they also have for the civil law kinds of cases, they encode the law. So for example, they have encoded, there was a demo I saw where they encoded the like emissions, European emissions from cars rules into SMT, and then they were able to answer questions around whether or not this car would be allowed or not. So there's I think a lot of work there that's quite interesting. What a lot of customers ask for, which is kind of what you're saying, is it is highly unusual that any complex policy from a university or from a corporation or from a city is even satisfiable. Highly unlikely, right? Like, because you just take the different parts from the different units and then put them in conjunction, for sure they're going to conflict. And so I actually think there's a lot of value in this tool for society and for organizations to just do the exercise of like, nope, your rules are unsatisfiable, just like, there's no way to even, to find and fix all those cases. I actually think it's very valuable, even if you didn't apply them to LLM hallucination. And then the other thing I think is quite neat is the idea of like, formalizing them, deploying them, and now you have a feedback cycle where you can see how people are using it, see the answers that people are escalating and saying that can't be right, and going to the administration, logging those, making a group decision, maybe transparently, like saying here's the policies and here's some examples. Maybe we used tokenization to hide some of the PII, but ultimately saying here were a bunch of cases where we're given the wrong answer, fix it, and then because you've logged all the Q&A pairs, you could go rerun the new logical encoding over the old Q&A pairs and see if you like the answers there. So it really gives a bunch of new tools for organizations to decide on what are the rules, and then for people to explore different ways to find all the sort of nooks and crannies of the rules too. So I think there's a lot to have that Gödel moment where it's like, aha, I found a hole in the U.S. Constitution kind of situation.
Any other question?
There's one back there and one there.
Hi, you showed all these different efforts inside AWS, what has happened in the space of automated reasoning, and it's a lot. So I was wondering if you could also, is there any meaningful way to quantify this? Like how many, let's say, lines of code or developers percentage-wise have had contact like with automated reasoning or formal methods in some form or another?
Yeah, so in a sense, every line of code, because we do a data flow analysis across all the Java code right now. But then we have Rust code that we've spent much more time on. But if you look at we have a proof of the correctness of the TLS handshake implementation in our TLS implementation. But then there's a bunch of code that doesn't contribute to that. So then there isn't a lot of deep reasoning on that code. But then some parts of it there is, and so it's kind of hard to slice and dice it. I would say overall the adoption of the tools has been quite low. I honestly can't think of a project beyond the data flow analysis and beyond the reasoning about policies and networks. If it required any interaction from the team to write down an invariant or anything, it didn't work. So there's a couple of teams that have, for example, that use Daphne that don't have scientists, and they're very unhappy. So the teams that have used Daphne that have scientists on board, it's they're not totally in love because there's a lot of brittleness and you change a variable name and suddenly the proof doesn't go through. But there's sort of we have tools and ways of, and there's a bunch of stuff we're doing to kind of address that. But the teams that don't have any scientists, don't have formal backgrounds at all, they're I don't understand how to use this. And so that's been, so for us, the Rust type system and the usefulness of the error messages, together with the rise of generative AI, is very exciting to us because we think it might make the tools much more approachable. So there's a lot of room to grow, let me say it that way. Yeah, so the way I pitch it all sounds very impressive, but go choose a random Amazon developer on the elevator and ask them what's formal methods. They're probably not going to know what you're talking about. Yeah.
Thanks.
Yeah, thanks for the talk. That was super interesting, and I especially like the point you make about soundness and soundness being important, and you make many good points. I agree with that. But one thing I often also struggling with when also trying to convince people about soundness is that soundness is often, or usually not an absolute statement, but a relative statement. That you cannot say this program is correct. You can say, I proved that this program satisfies the specification, maybe against this operational semantics. So there's maybe no problem in the program, but maybe the spec is wrong or operational semantics or something. So I was just wondering, how do you kind of deal with this, and how can you present stuff like this?
So that's where the soundness ops come in. A lot of the soundness ops stuff is whoa. What if the microprocessor is incorrect? What if your have you proved the correctness of your translation from Rust to Isabelle? Have you, and it's well, no. You're using these third-party APIs and you have this model of what those APIs are doing. Is it correct? Well, we don't know. And so that's often where the discussion is around, okay, well, how are you mitigating that? So for example, there's some work going on that we'll be able to talk about in some short amount of time. I can't talk about it today, but I can tell you what the tools they're using. So they are reasoning about Rust code that's been translated into Isabelle, but then there's questions around is our model of that translation correct, and so we use differential testing. So there's sort of, I would say, generally speaking, what we've done is we've found parts of the system that are really hard to get right and everyone's worried about. Or we've had, like, for example, in Amazon, in AWS, there's a Friday security meeting. So every Friday, we get together with the chief information security officer, and it's a very small meeting, it's about 10 people usually in the meeting, and we talk about the security close calls of the week, right? So someone's had a really bad day, and there's like data collected. We go and we explain what happened, we explain the mitigations, and we explain kind of why we're not going to be in this meeting again, right? And a lot of times formal methods turns out to be a mechanism. So often we'll identify the hard part to get right, and we'll apply proof to that. But then the surround will apply testing. And so yeah, so what we think about proof is it's really good at articulating what we know to be true and what we don't know to be true, but you can't know that everything is true. And so you kind of have to find a boundary and then say, beyond that, we're just merely trying to raise assurance that the surrounding environment actually respects the assumptions we're making. The other thing I'll say is that you see it growing. So we first encoded the semantics of the networking and policy language because the customers were having a lot of problems using it correctly. There's a bunch of like cases where customers were having really bad days because of security, because they had gotten it wrong, and so we wanted to make tools to help them. So we did that. Okay, great. And then we did a bunch of differential testing to validate that our model of that was correct. So we built, like, we had tooling to like go build a bunch of virtual networks and then see that the predictions we were making were correct with respect to the thing, and that was part of the testing regime. And then it was like, oh, well, now customers are asking, well, how do we know the code is correct with respect to that? We've done testing. Well, why don't we do proof? So then we go do proof of that. But now we're having to make a bunch of assumptions, like, because now we prove the correctness of the policy interpreter. But then it's like, well, how do you know that Dynamo is calling the policy interpreter in the right way? Oh, well, we're doing differential testing. And so, oh, now we're doing proof of that too. So what we've ended up doing is, I think there's a project called Daffodil where we synthesize the correct code for different customers of that interpreter, and then the internal teams are moving over to that synthesized code as opposed to their handwritten code. And then one could imagine that just continues on. So I think what will happen in time is you'll come in end-to-end properties. Like, this is what we told customers. They were able to reason about that networks. Now we know that the code correctly implements that, and then that hits the microprocessor. And we do have formal verification teams in the microprocessor team, right? So one could imagine like proving the correctness of the microprocessor in time. And so ultimately, but we will always ultimately have to trust the physics of the principles of physics, right? Like we're not going to go prove gravity.
Any further questions? You can speak up sometime. So it's not the case, and we still have the room out here too. So at the floor, sorry. So in case you feel more comfortable talking one-to-one to Byron, just come up to talk, and with that, thank you very much.
Thanks. Yeah, pleasure.